for the last part of this webinar, and we're going to hear from Renova's zinc recovery process by Karin from Chalmers University. So Karin, the floor is yours, and I would like to repeat, if there are any new people, please ask your question in the chat and they will be collected and asked at the end of the presentation.
Okay.
So Karin, please, you're welcome.
Yeah, thank you very much for inviting me. I will give a talk about our work with the zinc recovery from fly ash, and it's based on leaching and precipitation. And I will actually talk about from lab scale to full scale. So how come from the ash to final zinc product? And as you understand, this is not something you just do or prepare in a very short time, but it's been a lot of different partners involved. You can see them at the at the bottom of the page. But let's try to do this in 15 minutes, many years work. But just some words about Renova. You may be not familiar with it. It's a municipally owned company situated in southwest of Sweden. And we have actions from collecting waste to treat waste to incineration and landfilling. And I work there as a researcher, mainly focusing on ashes. And I'm also associated to Chalmers University of Technology, working with metal recovery from different materials. So our waste incineration, waste to energy plant, we incinerate about 550 tons of waste every year. And we have this advanced flagless cleaning, of course, and that gives us about 25,000 tons of fly ash annually. And today we treat this with physical and chemical stabilization, forming a so-called Bamberg cake, and then we landfill it. And before we landfill it in one of our own landfills, but due to new legislation some years ago, we send it for external landfilling in a landfill for hazardous waste. So why develop the ash treatment? I guess that's a rather unnecessary question to ask in this auditorium, but of course landfilling is not sustainable. And the landfilling is due to the presence of heavy metals and chlorines. So why can't we put it the other way around and use this as a resource instead? And as you might know, Sweden have a well-developed metal and mining industry. And as some metals like copper and zinc are present in amounts similar to workable ores, it would be a possibility for these industries to take the ash directly and treat it in their existing processes. But if you talk to representatives from that industry, they say that, yeah, ash, interesting, but it's containing slag forming and unwanted elements like silicon or mercury. It's also heterogeneous materials. Of course, depends on what we incinerate, and as it waste, it differs a bit from time to time. And these things together brings to the conclusion that the metal content is still too low, even though it's comparable to workable ores. So if we should utilize the ash, we need new technology. And I would say it's we in this industry producing the ashes that has to develop it. And I also would really like to focus on the second point here, saying that there is no real value in the metals until we have them in a usable form. Because I think it doesn't matter if you calculate on the potential value in the ash, unless someone wants to use it. The value is, nothing. So we started to see how could we try to do something and recover things from our ash. And from lab scale studies, we had seen that we had a lot of zinc, as we have heard before, and also that the zinc is rather easy to release from the ash. So we said that if we compare our business as usual, as you see at the top, where we incinerate waste, produce this Bamberg mix and landfill it locally, because that was what we did when we did this part of the work. Now it's external landfilling, as I mentioned before. But if we compare that with two different scenarios, the first scenario is that we recover the zinc and then sell this product to the zinc industry, while we take care of the ash residue, assuming we could still do a boundary mix and landfill it locally. In the second scenario, we recovered the zinc, but for the ash residue, we returned it to the waste incineration in order to destroy the dioxins. That has been some issue about in this conference. And then this re-incinerated ash residue will be transferred to bottom ash, and then you can potentially use it for landfill construction or other purposes. And when we compared these three different scenarios on economic and environmental perspectives, it turned out that this scenario was the most beneficial. And this is actually not anything new, because as you might see down in the left corner, already in 1990, it was a paper published about washing fly ash with acid and then re-incinerate the ash residue in order to destroy dioxins and other organic toxins. And I would say that that paper or that work is actually the basis of most of the technologies based on acid washing that's developed or under development today. And then you can ask yourself, why hasn't anything really happened until the last years? And I think, as someone was mentioning before, it's been too cheap to actually landfill things. So it's not been that interesting to develop technologies. So I think it's really nice to see that there are so many different initiatives going on right now. So the principle we developed at Renova together with our partners looks like this. We took ash from the electrostatic filters and then mixed it with acid from the wet flue gas cleaning. Mixed them together and then separated the ash residue. And then this residue you could re-incinerate, or you can treat it further to see if you could recover more things, or you can landfill it, depending on. Then you have the metal-rich leachate containing zinc and a lot of other metals. And from that, you could generate this high purity zinc metal, as was mentioned before. But we decided to, instead of doing this last step, that's a bit complicated and also could be energy intensive, to generate a zinc product. And in this way, we can do a zinc product, and we work with the ash. That's our major focus, and the metal industry could work with the materials that they are used to. So the challenges that we saw here was, of course, the quality of this zinc product. It must be good enough for the metal industry to be interested in it, as I said before. And we also wanted to assure that we decreased the amounts we landfilled, and also that we can treat the residues locally. So we set up a pilot plant, and here you can see a schedule of this. And I won't go through every detail here, but the principle is, as I said, we take ash from electrostatic filter and acid from the wet flue gas cleaning. So we actually use two wastes in order to generate something good. Then we mix it, we have a filter press and re-incinerate the washed fly ash. The leachate is collected and we precipitated the zinc. And then finally, we got this zinc product, that's a zinc hydroxide. And the overall zinc recovery rate was about 70%. And that's more or less exactly what we got when we did the lab work. So that's really nice. It's such a good correlation there. Some points about the different parts in the recovery process. And if we start with the washing, we saw that about 70% of the zinc was leached in the best cases. And for those who really focusing, you might remember that I just said that the overall recovery rate is 70%. And that's not a misspelling, it's actually true, meaning that the washing is the limiting step. The zinc you release will be recovered. An important parameters for this is, of course, the pH, but also the liquid to solid ratio and the leaching time. For the precipitation, we used sodium hydroxide to increase the pH and precipitated zinc. And the first time you opened this chamber filter and saw it was actually a zinc product present there, you got really excited. And then when we analyzed it and saw it was 50% of zinc in the best cases, it was, yeah, really, really nice. The second part in this project was to study this incineration of the washed ash residue. And as I said, it's to degrade dioxins. And as I mentioned, this has been tested before. So the idea is that you re-incinerate the fly ash and then it's transferred into slag. And the results we saw from this, we did it twice, was that more than 90% of the incinerated fly ash was transferred to slag. And for most elements, the contents was similar with or without re-incineration, but zinc and tin increased in some samples. But it's not possible to say, is this due to natural variations or is it actually due to the re-incineration of the fly ash? We need to evaluate it more in order to be sure. But we couldn't see any really large influences on either the fly ash nor the bottom ash. And that was what we expected. So now it's been decided that we should build a full-scale plant based on this. And you can see the timetable here. So so it will be up and running in 2022, I guess in the autumn. And the budget is about 9 million euros for this. I also had these specific questions and I thought it was easiest to answer them one by one. We didn't really see any technical challenges when we did this, and we were a bit surprised, but it worked rather similar, I would say, from lab scale to this pilot plant scale. But one thing that's important to remember is the storing capacity, because if you will have an unexpected stop in your process, you have to have a place where you can store your fly ash, because that's, of course, produced continuously. Possibilities and barriers for a wider application. I would say that this is a rather general technology that you could use for different kind of ashes and possibly also other materials. And this was also a bit discussed before. I think it could work for most ashes, but I think it's a large advantage if you have no lime added and if you have a wet flue gas treatment yourself, because then you will have the acid and you don't need to consume acid in order to neutralize the lime. Policy measures to promote fly ash valorization. I think that the legislation is not totally clear, or how you should adapt to the legislation. And I specifically think about the classification because it's it's many projects going on how to actually do this, how to classify it, and also that it's different between different countries, which can make it difficult if you should transport your material abroad. Sorry. So to sum up, we received about 70% of zinc recovery. In the best cases, it was about 88% of zinc hydroxide in the final product, and more than 90% of the re-incinerated fly ash was found in the slag. The potentials are sale of zinc product, decreased landfilling and decreased transports, and of course that we saves natural resources and and we also will be a part of this circular economy. And in 2022, hopefully we will have a full-scale plant. If you would like to read some more things about this, there are 2 reports in Swedish, free to download, a summary in English, and it's also a scientific article that was recently published in Waste Management. It's also free to download. So, thank you very much for your attention.
Thank you very much, Karin. So a few questions for you. I think you answered one of them. something about the recirculated fly ash. You said you didn't see any operational challenge, or how does it go with accumulation of various metals, corrosion, and these kind of things?
Yeah, of course, the corrosion we couldn't study during this short period we did this re-incineration, because the limitation was how much ash we could wash in our pilot plant. So when we didn't have any more washed fly ash, we couldn't do more testing. So of course, the corrosion we couldn't say anything about. And the other thing was about, yeah, recirculation of things. As I said, we couldn't really see any clear trends that this would not work. But to be sure, I think we won't recycle all the ash. Some ash will be landfill and some will be re-incinerated. But as we heard before in this presentation about fluvafluoric, it's actually done this recirculation already for many years, and it's working. So we're not so worried about that, but we will evaluate it more, of course.
Okay, yeah, because it might frighten some plants.
Yeah,
maybe.
And the reason why you wash it before is, of course, of the chlorines.
Yes. A question: you have customers for your zinc product?
Pardon?
What kind of customers for the zinc?
Aha, okay.
Product?
I can't go into that, but it's mainly secondary industries that work with secondary, or it's industries working with secondary resources.
Okay.
Yeah.
Yeah, we have heard about now, like you mentioned, fluvafluoric. So there are different technologies aiming at zinc.
Yeah.
Yeah.
So that's what I say. I think most of, or the technologies that's been presented here, where you have acid washing and recovery in some way, I mean, they are similar, but still each of the techniques have their own speciality. And I guess depending on your specific situation, one or the other will be most optimal for you.
So a specific situation, you mean local, national, technical, the kind of
that could be one
cooperation.
Thing. Yeah, but it could also be where you're situated, which kind of flue gas cleaning do you have? Is it another plant nearby? Yeah, but also, of course, natural legislation.
Yeah, yeah. So they have all their let's say niche or specific applications in this way. So, and competition is good.
Yeah. I mean, you can see it as a competition, but I think it's also
complementary. Yeah.
Yeah, because it's. I don't think it will ever be one technology that will be the best solution for everyone, because it's so individual in many ways.
Yes,
but that's my opinion, of course. Yeah.
No, I agree with this kind of specific situation. I think you don't have one silver bullet to fix everything at the same time.
No, then it would have been easy, and we wouldn't have any words.
Thank you very much, Karin. I think